So we'll continue with radical equations. These radical equations are going to be in the form of fractional powers. A fractional power is, in essence, a radical. This is a 5 power, so it's a square root of this to the 5th power. Similar to radical equations, I want to start by getting my rational power object isolated. So when I'm looking at this object, this equation that has this fractional power, and it contains x's to fractional power specifically. So there's x's inside to some fractional power. I want to get that thing all by itself. So anything either added, subtracted, multiplied, or divided by that thing need to go to the other side. So the first step of this problem is I'm going to take this positive 7 here, chop it off, and make it negative 7 over there. So that leaves me with my fractional power expression, x squared plus 5x plus 5 to the 5 halves power, equal to a new number, in this case 8 minus 7 is equal to 1. Now, in order to get rid of a fractional power, we're going to have to raise both sides to the reciprocal power of that object. So, when I look at this fractional power object that I have here, I want to raise this whole thing to a power, and the power I want to raise it to is going to be the reciprocal of that power, in this case the 2/5 power. Which means I have to multiply or raise that other side also to the 2/5 power. Now ideally, when we're doing this, the number here works out to some friendly number. Okay, if it does, great. If it doesn't, we can still work it out, just it won't be a very friendly answer. Recall a fraction of power is both a root and a power. Okay, so the 5th root of 1, 1 times 1 times 1 times 1 times 1 is 1. So the 5th root of 1 is 1, 1 squared is 1, so 1 to the 2/5 power is equal 1. Yes?
Is 2/5 the reciprocal of 5/2?
Yeah. The reciprocal of the power is what we're doing. So 5 halves power, reciprocal 2/5. Okay. And then just to highlight that with a number that isn't 1, suppose it said 32 to the 2/5 power. It doesn't, but suppose it did. 2 times 2 is 4, 8, 16, 32. So 2 to the 5th power is 32. So 32 to the 2/5 power is just 2 to the 2nd power, which equals 4. Right? So you take the root of the base to make a new base, and once you've taken the root, then you take that answer to the power. All right, and so on. It was 243 to the 2/5 power. 3 times 3 is 9, 27, 81, 243. Okay? That's 3 to the 5th power is 243, so the 5th root of 243 is 3, 3 squared equals 9. All right, so you evaluate the root first and take the answer to the power. That's how you evaluate a fraction of power that evaluates to a nice pretty number like that. All right, they don't always come out nice and pretty, but I would bank on most of the problems in that assignment should do something along those lines. If it was a different root, let's say it was like 27 to the 4/3 power. Okay, 3 times 3 times 3 is 27. So the cube root of 27 is 3, 3 to the 4th is 81. All right, so again, evaluate the root first and then evaluate the power of that answer. That's how you evaluate some number raised to a fractional power. So 1 to the 2/5 again equals 1. When you take a power to its reciprocal power, then these two things, the rule says base stays the same, this times this. Well, 5 halves times 2/5 equals 1. So we get this whole thing to the first power, better known as x squared plus 5x plus 5. In essence, the power and its reciprocal undo each other, leaving us with the inside bit. So just with radicals, this side with the ugliness is pretty simple to deal with. Now the leftover expression here is a quadratic expression. So whenever you have a quadratic equation, we're going to get it equal to 0. So I'm going to move the 1 over to the left. So we're going to get x squared plus 5x plus 4 equals 0. Then we look to factor the quadratic. This is a simple quadratic with a coefficient of 1 in front of x squared. So we simply need two numbers to multiply to make positive 4, that also add to make 5, which would be 1 and 4. So x plus 1 times x plus 4 equals 0. Which means x plus 1 equals 0, or x plus 4 equals 0. In each case, if you just move the 1 and the 4 to the other side, change the sign, we're going to get x equals -1 and -4. Just like with radical equations, these represent candidates for the correct solution. They are not necessarily correct answers. But of all the numbers in the world that exist, these are the only two that could possibly be right. We need to verify they're actually right by going back to the original problem before we mess with it, replacing x with these two numbers to see if it actually works out. So, I'm going to get -1 squared plus 5 times -1 plus 5 to the 5 power plus 7 might equal 8. Yes, we try this one out. -1 squared is +1. Be careful when you're substituting a negative number in for x and x is being squared, that sign and number are both being squared. Negative times negative makes positive, 1 times 1 makes 1. 5 times -1 is -5. So altogether, 1 minus 5 plus 5 makes 1, so we get 1 to the 5/2 plus 7 is supposed to equal 8. What's 1 to the 5/2 equal? 1, right? Square root of 1 is 1, 1 to the 5th is 1. So 1 plus 7 equals 8 is completely true. So that's a good answer. My other answer is x equals -4, so if I test that one, -4 in parentheses squared plus 5 times -4 plus 5 to the 5/2 power plus 7 is supposed to equal 8. What's -4 squared? +16. -4 times 5 is -20. 16 plus 5, 21 minus 20 is 1, so we get 1 to the 5/2 plus 7 might equal 8. That's the exact same thing we have up there, right? So it's 1 to the 5/2 still equals 1, 1 plus 7 still equals 8, so everything there is valid. So both answers work completely, so there's no extraneous roots in this problem. Both answers are correct.